Okay, so should we take one small break or do we just
Yes,
jump
and
into?
then we
Okay, so let's take another like 3 minute break and then we'll talk about type theory and then
Curry
announce
Howard.
our Curry Howard and then announce the like upcoming show that we're
Yeah.
preparing.
Cool.
Okay, let me. Why did I close that window? I needed it one more time. Let's see if we can undo the close tab. No?
Mm.
Okay, let me search for it again. So it's like timer. I guess we need a timer. There we go. So 3 minutes again?
Yeah.
I guess so. But this time let's start the timer. Okay, let's move to here. So yeah, let's have another short break. This time let's move the timer to what did I do?
Where is the window?
It's here. Okay, so let's do this. This time I'll start this timer when we go on break, not before. So let me put some music on. Is this the right thing? No, it's. Oh yeah, it is. Okay. And yeah, we'll be back in a few minutes.
Okay, see ya.
If your front door's locked, I'll come to your back door. If your front door's locked, I'll come to your back door. Let me in once, I'll be back for more.
Okay, we're back. Give me 1 second. Let's see. Kill this thing, and then we. Oh, let's swap. Go really.
Hi.
Oh, and they didn't stop the music. Wait, I think they can barely hear us. Wait, where's the music? Oh, I think it's. Oh, I think I know what it is. think it's this thing. Okay, sorry about that. That was probably
Sorry.
annoying. I'm sorry. Okay,
Hi.
cool. Hello, we're back. We're back. Okay, so now it's what? Curry-Howard isomorphisms, type theory, and an announcement. Cool. Right, so, I mean, we kind of already mentioned the Curry-Howard isomorphisms and how it got us closer together.
Well, from the scientific point of view,
Yeah. But yeah, I mean, it was...
Harry Howard saved the marriage.
Yeah, Curry-Howard saves marriage. Newspaper article. Oh, and then can you see the sun, like kind of like here? In,
But at least it's not in
at least it's
our
not in our
face.
eyes anymore. Yeah.
Yeah.
Right. So anyway, yeah. So it's so. I think at some point we weren't sure, but I think you found the proof that there's actually like this isomorphism is not just like
Yeah.
hand waving.
Yeah.
There's actually rigorous mathematical proofs that show that this is
Mhm.
an actual isomorphism,
Mhm.
right?
There is the handbook in Curry Howard isomorphism. It's a big yellow book, and yeah, you could formalize it. I mean, formalize what does it mean to have a deduction in logic, and formalize what does it mean to inhabit a type, and then just show that
So like
they are the same thing.
Okay.
And you could actually do it rigorously. So it's not just an
but-
idea that you just write.
But in
down.
that book, they're just proving the connection between type theory and logic. They don't go to Lambek at all.
Yeah.
It's no category
No,
theory.
Well, yeah, I don't think so. Yeah.
Okay. And like, do they move from type theory to logic, and then they prove the things in logic, or how does like I don't care what like not care, but like of course you can't tell us the specifics.
No, you just have to show that, okay, define what does it mean to inhabit a type, right,
Okay.
in type theory, and what does it mean to prove a
Mhm.
theorem in, for example, in natural deduction,
Okay.
right? And then you have to show that, suppose I can inhabit a type, and then just actually build a construction and show how you derive it.
But use the isomorphisms to move between the things, right? Because you like.
But you prove the isomorphism, so you don't use it.
Okay, but then how do you go from saying that something inhabits a type, which is a proposition in type theory, to
Mhm.
logic? How do you move between the two?
Of course, you define. Of course, okay, I got your point. You define what does it mean, how you move. What I mean, what's the connection between the types and the rules in the natural deduction, and then you use that to show that you have the same power. Of course, okay. So there is the first level in which you say what each component means. What does it mean to inhabit a type?
Like
What
the
does it mean?
translation.
And then how you translate from one another,
Mhm.
and then you prove that the translation gives you the
The same result.
result and the same power of
Okay.
deducing stuff.
Okay.
Right.
Interesting.
So it's not hand waving. It's actually
It's actually rigorous proof.
you could write it. Yeah.
Okay, but like for the longest time we thought that it's hand waving and not
Yeah.
a proof, and it looked super cool. It was super interesting. It felt like it should be more than
Yeah,
hand
in
waving,
more-
but we
in-
didn't.
In most
see the
materials
proof
you
yet.
look into, it's like also I mean, depends on at which level you want to go into. I mean, I'm passionate about this subject, and I look at some steps of the proofs, but it's, I mean, really.
The proof is not as interesting as
Yeah.
the result.
Yes, exactly. I mean, the beauty is in the result.
Yeah,
So
for sure.
Yeah.
Okay, cool. So then, okay, maybe. By the way, maybe we should just say the elevator pitch of what it is, right? Because maybe not everybody in chat is familiar with,
Okay, yeah, sure.
with what the
Mhm.
Curry isomorphism
Mhm.
is.
it's a really beautiful. Well, it's a really surprising
Result.
idea, right, or result, saying that three things, that they look completely coming from different worlds, that they are the same thing, right? So it connects what you could write as a program in functional programming, right? And you write a function and you write its implementation. Actually, that corresponds to proving that formula. It's actually a theorem in a logic, meaning that it's always true.
Mhm.
So this, for me, I mean, that's really beautiful, this result.
So in theory, that means that any program or function that you ever are able to write in a language such as Haskell, in a or like any other purely functional programming language which respects this sort of like Hindley-Milner or like some sort of like type theoretical formalism behind. But that includes Haskell, includes PureScript, definitely includes Argdyne, Idris, and Calc.
Well, I have a question for you here, but just go on, finish your idea.
I think that means that every function you write is a theorem, is a proof of it's something that's always true, right?
Well, I wouldn't. It means actually that, well, yes, okay, it's the proof for yeah. But my question is like, okay, you have a lot. I mean, I know the result for simply type lambda calculus, and then I know some hints that you could the connection between modalities and monads and so on. But is it? I mean, can you do it for everything you could write in Haskell?
So that's a very
I think
complicated
it's
question because
I mean,
Haskell is very complicated. Haskell has a lot of extensions. Like there isn't even one Haskell that you can talk about. Because is it Haskell with is it Haskell 98, which is a very very shouldn't be any language which uses simply typed lambda calculus. Well, okay, that's definitely the simple answer,
that's
right? If you write an STLC language,
but that's true. You can do it, but then maybe you have extra.
But then like STLC doesn't have recursion, right?
Yeah.
So then okay, but like you can't not have recursion. That's very important. But then you don't have higher kind of types. Or it's very fun to have higher kind of types, right? Because otherwise you cannot define functors. Because like functors require a higher kind of type to be able to say you have a list of things, right? Or a maybe of things or whatever. You can't have a fixed point. Okay, you could define a fixed point axiom, right? But
I was more into, because when I hear you speaking, I hear this a lot of keywords that I don't like. I don't know. Let's say something complicated that you use in functional programming.
I so like profunctors,
stuff like that. Exactly, things like this. Okay, do we know that they are they all have a correspondent through Curry-Hauer isomorphism, or
so? Okay, these are all has the Y Combinator. Yeah, I think so. Oh, does it? Is it well typed in STLC? I'm not 100% sure it does.
What's the?
It's a like recursion combinator.
Okay.
I'm not 100% sure. It might have. But anyway, I think the idea is like, for example, profunctors and comonads and free interpreters or whatever we want to say. These are all higher kinds, like they're all primitives in Haskell, right? So I think the idea is let's figure out what primitives we need to use in Haskell and then see if they are,
okay,
right?
I understand.
Because like the primitive is like for, I don't know, profunctors, it's just higher kind of types and functions pretty much. Right?
Okay,
that's all you need to build that. So can we have like, what do we need for higher kind of types? Well, we need like, it's not LSTLC because that's just like the simplest thing, right? So you need type variables and you need, I don't know what else, like higher kind of types, right?
Okay.
And I think it still holds, right? It's pretty easy to prove with that. But then there's a few things that, like for example, monads and I'm not sure because I think I'm not 100% sure that monads require anything extra.
Yeah, but monads, they have a correspondent, we know.
Yeah, but yeah, they do, of course. So yeah, I'm not sure type classes, for example.
Maybe we're not the ones who could answer this question, but
yeah, I mean we'll probably read and do something around that at some point.
Yeah.
But but I think the idea is that I think that still is true for even for Haskell and all of the advanced concepts, and I don't think it's very hard. Okay, again, not as hard as proving each advanced quote-unquote topic translates to logic, right? Because you don't have to do the isomorphism between autocomonads and logic, right? You just need to figure out what's the primitives I need in order to build the comonad, and if those work, then the comonad should also translate.
Yeah, I'm asking this question because from the logic,
the correspondence holds for total functions. Something in IO might not be total. Yeah, probably. I think so. Like bottoms is a tricky subject in here, right?
No.
So can you? I'm pretty sure you should be able to encode bottoms as well as logic, right? Yeah. So just.
I think the idea is you move from what they call minimal logic to you actually go to intuitionistic logic, which has bottoms. So.
Okay. Yeah, so,
Yeah.
so I think that they're definitely, and again, I'm definitely the logic expert is not
Well,
me.
no, I'm not.
but-
But I'm asking this question because when I heard about this wonderful idea and so on, and I thought, okay, cool, so I can translate stuff from logic to type theory and so on, and then okay, I'm thinking about the stuff I know from logic, okay, and we know we have different
Types of logical.
of course this, and then but we also have different types of derivation, not just natural deduction. We also have different. Okay, what's the connection to logic? So I'm curious what we can move from logic to type theory, and then that's why I'm asking. Okay, what can you move from type theory to logic, and as well. So that's why I ask you this. This
Yeah,
question.
I mean there might be a lot less because type theory is relatively new to math, right? Compared to logic. Logic has been there for forever, right?
Since Greek ancient.
Right? And then type theory is the new kid on the block, right? Relative to math, at the very least. But yeah, there might be because like there's a lot of interest in type
Yeah,
theory.
but
Maybe even-
intuitionistic logic is what in the beginning of is the 90s, right? So
you tell me.
yeah, it's
It's still new.
1934 or
Okay.
something, 30
Okay.
something. So
Yeah, interesting. Like again, I'm pretty sure that there could be a lot of cross like pollination that maybe not a lot of people are considering, and especially maybe I think you're
Because-
right, especially probably in intuitionistic logic. Because I don't think there's a lot of like there's these constructive mathematicians who are interested in this sort of thing, but that's a very small. Like there's not a lot of them, right? There's not a lot of mathematicians interested in constructive mathematics.
mathematicians probably know, right? So yeah. I know, for example, some logicians, they take some. Okay, you take some rule from a natural deduction or a secant calculus and so on, and you say, okay, what does it correspond to type theory and to programming? And maybe sometimes we force a bit the interpretation we give. So Curry-Howard isomorphism, from my point, is so beautiful because it's so natural. Nothing is forced there. You don't search for an interpretation of the conjunction. It is just a sum type and so on. And sometimes I think when you try to translate from one area to the other, you just maybe something is artificial. It can become artificial a bit, forced a bit, right? So that's why I was saying, okay, what's natural? So yeah.
Yeah, and again, like this isomorphism is not the result of I'm in logic and I will force some sort of
Yes,
type.
exactly. What
it's like-
should I do there?
It's like people look back and like, oh look, those two are the same.
yeah,
these two
and
are
then
the
you
same,
feel
and these two are the
sucker
same.
on your forehead, right? Like, okay, it's been there since forever, but you just
But
didn't see it like
apparently
this, right?
there's been like legend tells that this has been known for like 60 years.
Yeah,
or something,
nobody
right?
wrote
but
it.
nobody wrote a paper
Exactly,
about it.
exactly.
But they're like, okay, people.
It's
like,
common sense. I mean,
Yeah.
it's so trivial. I feel ashamed to write this
Write a
as a
paper
note,
about this,
right?
yeah. So let's see. We have a few. So if you look at a categorical perspective, you might be able to move a lot of stuff. Yeah, that's
Yeah.
possible. That's very possible to be true. And sequent is linear types, I think.
What's sequent? Sequent, like
Do you mean like sequent calculus or like some other meaning for sequent? Because it's funny you should mention sequent
jam.
calculus.
Yeah.
Because this is your jam, right?
Well, no. Trying to convince you not to.
No, but like you really like the idea of sequent calculus in logic, right? And it's like a way.
It's not
to-
that I like it. It's more healthy. Not healthy. Not necessarily.
You
this.
heard it here first. Natural deduction can.
Sequent calculus, yeah.
Okay.
So I was pitching this idea to Vlad recently, and I was trying to convince. And well, we take our daughter for a walk, and then we start to speak about math. And I was trying to convince Poor kid. I was trying to convince him that okay, you shouldn't use natural deduction. You should use sequent calculus. And I was trying to sell it. I think it took like I was preparing every day for the next walk how I should convince him. I think I convinced him at the end, so that will be the experiment we want to do. But
Oh no, that's the second part. So
yeah, but the idea sequent can correspond to a linear type, but not necessarily. So you can define linear types correspond to linear logic, right? As for example,
In the Curry-Howard
in the
isomorphism.
Curry-Howard isomorphism, if you look at simply type lambda calculus, that corresponds to
Intuitionistic logic.
or the minimal logic, intuitionistic logic without bottom necessarily, right? But okay, and in the Curry-Howard isomorphism, it is stated in from the logic part they use natural deduction, right? This is how they do the parallel between the rules. They have the rules for natural deduction, and then they have the rules for the type theory. The beautiful part is that in logic you have different ways of expressing when you could prove a theorem, or you could find the proof, right? As you do in natural deduction. And secant calculus is another way of solving this problem. So you have natural deduction, and then you have secant calculus, and of course they have the same power. But secant calculus have better some better properties, and you could define secant calculus for any logic you want, right? So you could define for linear logic, and then you would go into linear types, or you could define secant calculus for intuitionistic logic, or for classic logic, or for modal logic, and so on. So every logic will have a secant calculus. So that's to answer that point. And the idea is that if you want to go to theorem proving, secant calculus behave better than natural deduction. There are some rules in natural deduction, like for example modus ponens, right? The one in which you eliminate the implication.
Okay.
Okay. In which, what does it say? It say, if I know A, and then I have A implies B, then I can prove B. But usually when you want to prove your theorem, you go from...
Yep.
Yeah.
That's one of the problems.
Yeah, it's not algorithm. You cannot write an algorithm, and this is what I was exactly what I was trying to say. That in this rule, for example, when you in modus ponens, usually when you want to prove your theorem, you start from the bottom, right? And you go from B and say, how do I prove? So I need to find an A, right? And you have to guess what to plug in there. With secant calculus, if you have, of course, there are some if in a good secant calculus, let me say like this, you don't have to guess anything, and that's
it's a clear-cut algorithm. You don't have to.
Yes, you don't have to guess anything. So, and then, of course, you ask, but what type theory corresponds to secant calculus? And you get a type theory which is equivalent to simply type lambda calculus, but the rules they differ. They may differ.
I'm curious about that. And I guess this is a good time to start talking about the show we're planning, maybe.
Yeah, so it's your show.
Well, it's our show. But
it's your show.
Okay, anyway, no, it's our show. Come on.
Okay.
It's our show. Please. Right, so starting this Tuesday, we'll start we'll do a weekly show together where we do stuff. Right, and then for the first few shows, we'll see how much time it takes.
It will be a show in which we try to put more theory, more logic.
Yeah. We do it will be, but we also write stuff, right?
Yeah.
We're not going to talk, so we'll be writing code. It's not. We'll be learning stuff and writing code as we learn stuff, right? So it'll be a practical approach.
More writing code.
Sorry.
More writing
code and everything. I think the camera is flipped, so I don't think you can read this, but I think most of you will recognize just without reading it. So we'll start. It's flipped. So we'll take the Tapple book and we'll go from the simply type lambda calculus there, and we'll implement it. And I recognize the book. I'm sure. So we'll start with the simply type because we don't really care much about untyped, right? We're not going to waste time on that. So we'll start with a simply type lambda calculus, and we'll write an implementation, like a simple one in PureScript, I think. And then the cool thing that we'll do after that is, we'll write a parser and an interpreter, right? And then we'll write a couple of functions just to make sure that it works and so on. We're not going to formally verify it.
No.
But we are going to try to do proof search,
yes.
Right? Which means that which is kind of like exactly what the coincidence I'm working on my lambda calculus in PureScript right now. Cool.
Yeah, nice.
So the idea is to write proof search, which is exactly the kind of thing that if you've been following Haskell recently, Reed and Sandy are working on with trying to find an implementation for a function, right? For a type, for a known type. Although we'll have a more theoretical approach than that, and that's your area, right?
Yeah, so the idea was this, to use the Curry-Howard isomorphism, and instead of going to the natural deduction, we will use the sequent calculus. So we will have a good algorithm, right? And suppose we will implement it to be fast, in which we will obtain a proof or all the proofs for a certain formula, and then we will translate that proof from the sequent calculus into, okay, we can go in natural deduction, and then from natural deduction to go to back to type theory, and use that as all the implementations possible you have for your function.
Yeah. So we're starting this Tuesday, right? So 2 days from now, it will be the first stream. I doubt we'll get to implementing a lot of that in one day. I think we'll barely be able to do the lambda.
We will start with the simply type lambda calculus.
I think for day one it will be parser, interpreter, and probably that's it. I don't think we'll have time to do more than that.
And then we can start to implement the sequent calculus, and then make that run as a theorem prover on its own.
Okay.
And then move that, make the translation, right? Use the result from the theorem prover from sequent calculus and translate it as an implementation for the functions in simply type lambda calculus.
Cool. You can so I made a lambda calculus parser less than 15 minutes.
So
you can find this outside of FP. Yeah, sure.
Yeah.
I agree. Like parsing in FP languages is very nice, and then there are some libraries which simply take the cake there.
Yeah, I'm really interested to see how fast the theorem prover will be, and how
it will be hard to compare it with anything, right? How do you what's fast?
Yeah, I know what you mean, but I'm just looking forward to see how the proofs will be, and how we get all the proofs, and what we can move back to the type calculus. So.
Yeah, sure. I think there'll be some yak shading and bike shading along the way. Like maybe we'll try to write the proofs nicely with a pretty printer that looks nice and so on. Like maybe we'll have some fun, right?
So I think the final goal will be to.
Okay, so initially the final goal is for STLC. Let's be able to write any sort of function and get a proof for it, right? Which means the implementation.
Get all the implementation.
Yeah. So write a what's it called? Write a a type and always get all possible implementations, and then the write a Twitch bot. Yeah. Okay. I deserve that. You can get all implementation for it. Yeah, I think you can. You can for STLC. I think we can.
Depends on the type. I mean, yeah, for simply time lambda calculus, yes.
Well, sure. I don't think
depends. If you get.
Is there a type with infinite amount of implementations in STLC? I don't think so.
Yeah, but if you have just LTLC, just simply type lambda calculus. No, they are not. But if you, for example, in Tuple, they put naturals. Okay, then there's
sure.
Infinite.
No, okay. So I think what we can do is whenever we reach things that can become infinite, actually, I think you can have infinite implementations even in simply typed. I'm not sure, but as soon as you have something that, as soon as you have type variables, you can have given an a and the function from a to a giving back an a. You can apply it once, you can apply it twice, you can apply it as many times. So this kind of begins to be equivalent with naturals, right?
I mean, of course, for example, if I want to prove the a implies a, right? In sequent calculus, you will get one proof. And with that calculus, so we would avoid, because of course you can write a proof which, I don't know, has circularity in it,
loops or what it does,
loops and so on. But in the secant calculus, you eliminate all these all these effects that you don't want, right? So
but again, we don't have side effects.
You get the normalized proof, so you get the smallest one.
Yeah, I think so. I think you're right, Bolt, there. So anyway, we'll start here. We'll get this done, which I think we're pretty sure it will work, right? We think we're not It's just an algorithm for like sequence calculus, right?
Yeah,
That's what sequence calculus does.
Sequence calculus.
And then after that, we'll try going through the types and programming language to different types of like complicate the type theory as much as we can until it stops working, I guess, right?
Yeah.
We'll see. Maybe we can get recursion in. Maybe we can get.
We
I
can
don't
look
know.
at monads and model logic
Like,
as well.
We'll just go through types and programming languages, and if we think of things that are not there but we'd like to do, we'll just add whatever we feel like, right? But I think just STLC will take us at the very least 3 shows, like 3 weeks or something. Plus sequence
More.
calculus, plus at the very least 3, if not more.
Yeah.
Right. So we
Maybe
already
more.
have a plan for like 1 month.
Yeah.
So.
Yeah.
So we'll see as we go what we find interesting, what works and what doesn't. But that's the plan for the near future.
Mm-hmm.
So yeah, and I think once we're done with this, we'll figure out some other cool stuff, like maybe work on the logic that I've mentioned for quick check, for quick strong,
Yeah.
and whatever. Maybe we can look into category theory at some point, but
Do some
anyway.
exercises together.
Yeah, but we'll focus on this for now.
Mm-hmm.
Okay, cool. Well, I guess
Let's check the baby.
that's kind of it. Yeah. Yeah, we need to see if the baby is still alive, right?
I think it's alive, but I think it's not napping. So
Yeah. Okay, don't worry. She's with my mom, so it's fine. It's just she's probably missing us by now.
well, at least I miss her. So
I thought you were going to say at least missing me. I'm like, oh come on, don't be so mean to me. But that's definitely true. She's she's at that age where mom, like she only wants to her mom, right? Lucky. Well, anyway.
so sequence calculus.
Yeah, sequence calculus. That's it. Okay, so I guess that means we're done for today.
Mhm.
I'm going to we're going to stop the stream now. I'll see you guys tomorrow for sorry, not guys, you folks tomorrow. I'm sorry. For PureScript Mondays, we'll do PureScript. All right. We'll look at some news. We'll figure out what we'll do. We'll do some PureScript for sure.
So the show the show with the tuple will be on Tuesday.
Yeah, and Tuesdays, every Tuesday we'll have this
How is called Tuesday type theory?
yeah, Tuesday type theory Tuesdays or something like that.
Okay.
Yeah, TTT.
TTT.
And then that's the plan for the next few days. So yeah, I'll see you in a couple of days then. Well, I'll see you tomorrow, and we'll see you together in 2 days.
Yeah.
Yeah. Well, thank you all for watching.
Thanks
and,
for watching.
I'll see you soon.
See you.
Bye-bye.
Bye.
Yeah, thank you. Also, again, sorry for not mentioning it, but thank you, chat, for being very
it was a really
engaging.
nice
It was fun.
afternoon.
Yeah,
It was a
And
fun afternoon.
thank you for being nice. Because, like I said, Didi was very.
I'm still nervous, but
Still
it's
nervous?
okay. Yeah.
Well, it's gonna get better.
Yeah.
Okay. Well, yeah. Thank you very much for all your questions and the interaction. That's what makes it fun, right?
Yes, exactly.
Like if it wasn't for chat, we could just do it outside with the baby, right? While
Walking the baby. True.
Okay. Well, yeah. Thank you
Okay.
again, and I'll see you tomorrow.
See you. Bye.
Bye bye.